Hello everyone. We will be solving question 44 of GATE 2019 Chemical Engineering paper from the subject of heat transfer. The question is 20 centimeter diameter cylindrical solid pellet of a nuclear fuel with density 6000 kg per meter cube and conductivity of 300 watt per meter Kelvin generates heat by nuclear fission at a specially uniform rate of 10 raised to 4 watt per kg. The heat from the fuel pellet is transferred to the surrounding coolant by convection such that the pellet wall temperature remains constant at 300 degrees Celsius. Neglecting the axial and azimuthal dependence, the maximum temperature in degrees Celsius in the pellet at steady state is dash, rounded off till nearest integer. Okay, so here we have been given that axial and azimuthal dependence is nil. Okay. That means that in the energy balance, for the energy balance equation that we write for the cylinder, all the terms corresponding to z and phi will be equal to 0. So that is, we can write the energy balance across the cylinder. So let's just consider this cylinder. This is my center, and we have been given r over here. So this is at r equal to 0, and this is r equal to r. This is my z. So we can write the energy balance equation as 1 by r d by dr r plus we also have this heat generation term, so that is q dot is equal to 0. So this energy balance we have to use to find the maximum temperature in the pellet. But since we are given steady state, so del T by del T we are considering it as 0. And here what all things we have been given, the diameter is 20 centimeter. That implies r is 0.1 meter. Density we have been given as 6000. Conductivity K is 300. Now Q we have been given as 10 raised to 4 watt per kg. And the pellet wall temperature we have been given as 300 degrees Celsius. And we have to find Tmax. So let's just solve this equation to find the temperature profile, and once we have the temperature profile, then we can differentiate it with respect to r to find the and equate that equation to 0 to find the maximum temperature. Yes, we can simplify this and write it as d by r rk q into r is equal to 0. Now we can integrate this equation with respect to r once, and it will give us rk dt on r plus q dot will constant, and the integration of r will be r square by 2. This will be equal to c1. Now let's just find the value of c1. So that is at r equal to 0, that is at the center. We can put the value of r equal to 0. So this will become 0 plus q dot into 0 is equal to c1. So that implies that c1 will be equal to 0. So yes, we can write this as r k plus q dot r square by 2 is equal to c1, and c1 was 0. Now we can again simplify this and write it as this r will get cancelled out, that is dt by dr is equal to minus of q dot r upon 2k. We can again integrate this equation with respect to R to find the temperature variation across radius. So that will give us T is equal to minus of Q dot into R square on 4K plus C2. Now we can use another boundary condition, that is at R equal to capital R, that is at the radius. We have been given the wall temperature as TW. So we can write that as TW is equal to minus of Q dot R square upon 4K plus C2. So from this we can find the value of C2 and put it over here, and we can get the temperature profile as T is equal to TW minus of Q dot R square upon RK plus Q dot capital R square upon, this was 4. This we can simplify and write it as so from this equation we have the temperature profile across radius. Now for maximum temperature, we can write that dt by dr is equal to 0. So we can just differentiate this equation and equate it to 0, and we can get 0. Tw is constant, so it will become 0 plus Q dot R square 4K to differentiation of 1 will be 0 minus of integration of x square will be 2x and 1 upon r. So this term can't be equal to 0, and also we have been given that r the radius of the pellet is not 0, so this term will only be equal to 0. So from this we can get that at r equal to 0, T will be T max. So to find the maximum temperature, we can put the value of r equal to 0 in this equation. Also, since the cylinder is symmetric, we can just straight away remember it that for any symmetric object at the center the temperature will be maximum. So yes, we can put r equal to 0 in this equation, and we can get the T max as TW plus Q dot R square upon 4K. This will be 1 minus of 0. Now we can just replace all the values. So the wall temperature we have been given as 300 degrees Celsius plus Q dot we have been given as 10 raised to 4 watt per kg. So yes, let's just write it as, now this I need to change into suitable units, so I will just multiply it by the density 10 raised to 4 into 6000 on 4 into k. We have been given as 300 into radius we have been given as 10. Diameter is 20 centimeters, so radius will be 0.1 meter, 0.1 whole square. This will be equal to 300 plus 500, and T max will be 800 degrees Celsius. So yes, the maximum temperature in the pellet at steady state will be 800 degrees Celsius. With the final answer rounded up to nearest integer, we can write it as 800 degrees Celsius.